focuses on advanced structural systems and design methods, including steel and composite structures, hybrid solutions, facade engineering, circular and demountable construction, and digital fabrication. He is the author of peer-reviewed publications, holds an international patent, and has received several scientific recognitions, including a Future Paper Award from Estruturas, Elsevier, and a Best Paper Award at International Conference of Thin-Walled Structures in 2023. He is listed among the world's top 2% most cited scientists from Stanford, Elsevier, and he is also a board member of the Portuguese Facade Engineering Association, actively contributing to the integration of academic research and engineering practice. So please, Rohola, the floor is yours.
This one is to go. No, this one is to go. This one's back. But this one is to go. Thank you. Actually, it's so difficult to speak after such a nice presentation. My name is Rohola, and I want to start my talk with an appreciation and an apology. So I appreciate Professor Caldas for the invitation and the organization team for organizing such a good event. Also, I want to apologize for the audience that you have to be patient with 1 hour talks in English. I promise that the next presentation in Brazil would be in Portuguese, so I need to practice for that. I would like to say that this is my first visit to Brazil and Maringa. However, my history with Brazil is about 30 years. So I'm going to explain this history briefly. I born and raised in a small town in a corner of Iran. So when I was 5, I don't know why, but I just fell in love with a football player at that time, that his name was Bebeto. Maybe because his name was so easy and nice. So when I was 5, I knew that I am an Iranian and I like a football player from Brazil. But 25 years later, or 20 years later, I moved to Portugal to continue my education at the University of Coimbra. So in 2020, during the pandemic, I was alone in the lab and I was preparing my tests. Some of them I will explain here. And then a student, a Brazilian student, just entered the lab. It was his first day. That student was José Filho. So later he told us that we have to call him Zé. 2 years after that, I went for a short visit to Luxembourg and I met another Brazilian from Maringa, that is Adriano. So they both talk about their supervisor and colleague from Brazil, and they introduced Professor Caldas. So I met Professor Caldas in CMM conference, and immediately we became friends, like we have been friends for a long time. So in CMM conference, I met also Professor Luciano for the first time. And then after CMM conference, he said that see each other next 2 years. But 1 week after that, I went to Hong Kong for a conference with Professor Da Silva and Professor Elena. And there I met him again in Hong Kong. So in Hong Kong also he said that, well, probably we see each other next 2 years. But here we are after 3 months in Brazil and I met him again. So let's move forward to the technical part of my presentation. I will talk about an innovative structural solution using cold-form steel and lightweight concrete. So this is a system that we proposed last 2 years to investigate this system. Basically, this slide shows everything about my presentation because we investigated the column, the beam, and the connection. So this was our objective, to present an innovative system using cold form steel and, of course, lightweight concrete in order to be prefabricated, sustainable, and cost efficient, and also suitable in terms of fire resistance. So for this purpose, we tested column, beam, and plug and play joints. So for the column, we performed test simulation and design under compression and fire. Then for the beam, we tested under bending effects and also subjected to elevated temperature. Now, let's move on for the first chapter, which is a composite column. So our research team in this section was Professor Elder and Professor Rui Simões. And then I received a significant help from these two technicians, Vidal and Miguel, from University of Coimbra. So the composite column that we presented was, there we used three types of cold form section, not three types, three sections that we call it U-shape, C-shape, and sigma. So we built the section and we fastened the, so we had built up section using self-drill fastener and then filled with concrete, with lightweight concrete. Here is a photo of the section, experimental test that we prepared in the lab. We tested two types of column in terms of slenderness. Column with 1 meter, approximately 1 meter, and we use the universal testing machine. And then we tested 3-meter columns to see the effect of two slenderness. So for that, we assembled a test setup for the 3-meter test. Here is a buckling failure mode of the short composite column. You can see that the failure mode in almost all of the section was due to the local buckling, which was expected because we are testing short column. We had one challenge that maybe you see this column is somehow like without any deformation. Actually, this was the first test that we did, and we didn't have a proper boundary condition because the section of the column about 1.5 millimeter, and if you don't have a very, let's say, smooth surface to transfer the load from the machine to the concrete and steel at the same time, you will have crushing here at the boundary condition. Therefore, we clamp the column from the both sides in order to protect the boundary condition of the column from early failure modes. Also, we tested the column without concrete, basically bare steel, okay? The reason that we did this was first to see the behavior of the cold form steel sections. Also, later on, in order to propose equations to determine the capacity of the composite column, we decided to do the test to see the contribution of the cold form steel section within the composite system. Also, we wanted to know if the cold form steel section within the composite system, the behavior improved or not compared to the steel section itself. Here also is a failure mode for the long composite column. You can see that for the rectangular section in the left, the failure mode is due to the global buckling. And for the right side, because we had a bigger square section and the slenderness was less, we had buckling failure mode due to the interaction of local and global. Okay, so we tested 36 column, including 24 composite column and 12 bare steel column. And then we went for the calibration to have a reliable model that can well predict the behavior, because later we can extract some data from the models that we cannot extract it from the test. So here you can see that the simulation well captured the failure, the loading, the capacity, and the behavior. After having the understanding from the test and also calibration, we perform a parametric study on the composite column. But here we have different, only these two sections, but these analyses were only for stop column because we wanted to know the plastic resistance of the composite column, not for the long column, okay, just plastic resistance. So we designed the stop column in order that their non-dimensional slenderness be less than 0.2 to have the plastic resistance. Here is a typical failure mode. Of course, this is exaggerated because I scale it by 2 to see which part of the composite, which part of the steel section has buckled. So this buckling shows that the inner side of the steel section remained without local buckling. Only the outer surface of the steel section buckled. So we are going to use this later, okay? So we basically ran 1,300 simulation with 2 different steel grades and 3 types of thickness, 1.5, 2, and 3, and also the profile with height, the profile height of 100 meter from 300 meter. The reason for this range was that this is the range of the cold form section that we have in Portugal and Europe. This is more or less the range. So first, we compare our it is difficult to stay in this. So we compared the result first with Eurocode to see if the Eurocode approach is applicable for this type of section. This section are not existed in Eurocode 4, so we just checked the Eurocode 4. And Eurocode 4 generally is for class 1, 2, and 3 section, not for class 4 section. And the equation in Eurocode says that you have to consider gross cross-sectional area. While we have class 4 section here, we check the gross cross-sectional area. And you can see that these results are only the contribution of steel. So we don't have the effect of concrete. We have the effect of concrete, but we don't have the contribution of concrete, okay? So we compare the result, and you can see that the prediction fall in the unsafe zone, which means that the prediction that we calculate according to Eurocode 4, if we consider gross cross-sectional area, would be much higher than the test, which is unconservative. So also there is a paragraph in Eurocode 4 that says that if you have local buckling, you have to take it into account, but doesn't explain that how we can take it into account. Therefore, we consider the whole cross section as effective cross-sectional area. We calculate it for the whole section, and you can see that the results are in the safe region with a very you can see that the result is is way more less than the experimental test and the simulation. If you remember from this slide, we said that the inner section remained unbuckled. So therefore, according to this, we classified the section that the inner core, which are colored here in blue, we consider gross cross-sectional area for that, and for the outer surface, which are in red and green, we consider effective cross-sectional area. But this is a famous formula that majority of the codes is based on, that is for the buckling of the plate. We solved this. Basically, we extracted the load contribution of each edge of the section, and we solved this equation. And then we modified the buckling shape here, buckling factor here. And then we calculate the resistance of the steel section within the composite system and compare with the test, with the simulation. So here you can see that the contribution, the steel section resistance is with a good agreement with the simulation, according to this new modified calculation. Also, we extracted the contribution of concrete now. Eurocode suggests 85% of the resistance of the concrete to be calculated, and says that with some modification you can consider one. We just examine here, and the result shows that the factor of 1 is fair enough to calculate the resistance of concrete within the system. So finally, we compare the plastic resistance of the composite section and compare with the simulation. Here you can see 1,300 simulation shows that the resistance of the finite element over the prediction is around 1 with coefficient of variation of around 4, which is acceptable. Also, we did more or less 7,000 simulations for the slender column, and we compare it with the buckling curve according to Eurocode. And the final conclusion is that buckling curve D is more accurate for such a composite system. Now we tested the same columns. It's hard to say the same column, but the replicated of the other column subjected to elevated temperature. The team were the same, only Professor Louis Lame, who is expert in fire, added to the team. For the test setup, we also had a setup that we built it, and also somehow we cover the specimen with electric furnace that we have at the University of Coimbra. So we had two types of tests, short one and long one. So I'm going to explain the buckling and failure mode later. Now I jump and briefly go to the simulation and calibration. So the failure mode of the long and short column were local buckling of the steel section. Here you can see that for the short and for the long column, the failure mode was due to the local buckling. Then we perform heat transfer analysis in Abacus, and we compare the result of on the surface, the temperature evolution on the surface of the steel section and inside of the concrete, for the short one and for the long one. Of course, we measure the temperature in many levels of the column, but here we are presenting in the mid-level using the thermocouples that we had. Then we perform a fire resistance analysis, and we compare it with the experimental data, which is in a very good agreement. Also, we compare the elongation, because the elongation of concrete and steel is way different, but within the composite system is so difficult to capture it. So we check the elongation of the composite system and compare it with the finite element simulation, which were in a close agreement. Also, we compared the result with Eurocode, and according to our calculation, if we consider effective cross-sectional area and buckling curve D, we are in a good agreement with Eurocode 4, part 1-2. So we had two challenges during the test of the for fire test. Here you can see the buckling of the fire after test. And you see that the local buckling is here in all sections, but here we have explosion in two of the sections. So I can explain the story of this explosion. This explosion happened 30 minutes after that the test was finished. So we had the test, we saw the fire resistance, and then the furnace was closed. I went to my office, which was very close to the lab, and then after 30 minutes, we heard like a big explosion. Then I said that, oh my God, I want to be promoted by Professor Da Silva. I don't want to be fired. So we have to analyze because we are going to damage the electric furnace. So my colleagues say that we have to probably warm up the column in order to release some of the moisture. So we did that for 8 hours with the temperature of 50 degrees just to warm up the column. Then we did the test, and I said that, look, this is a possibility, but we have to monitor it. So I was close to the furnace, and then I was monitoring, and so after like 30 minutes, again, it was an explosion. And then I said that, oh, for sure, I'm going to be fired. So, but during that monitoring, I realized that because the furnace was so hot, we could not open it immediately due to the safety. But what kind of safety? We had explosion after. So when the furnace was closed, the air temperature was about 700 or 800. So to make a balance, the temperature of the concrete inside was about 70. So after 30 minutes, the temperature of the air went to like 500, and temperature of the concrete increased to 200. That's why we had the explosion. So we decided for the test later to open the furnace slightly, and we took the risk to open the furnace slightly, and then we didn't have explosion in the next test. Here also is an image of the cold form steel section without concrete, and you can see that the failure mode is that basically the steel, thin wall steel was somehow melted. Another challenge later in design that we had in composite column was that if you design composite column according to Eurocode 412, you need to have heat transfer analysis, and then you have to divide the concrete section into the different layer with the somehow uniform temperature, and the calculation is complex because you need the heat transfer analysis, and heat transfer analysis is not easy to be performed. So we defined a task there. We have to tackle this also. So we did 302D simulation of heat transfer analysis, and you can see here that the temperature in the inner core of about 50% of the edge and the outer core is somehow uniform. So we presented an empirical formulation that can measure the temperature within the time for the core of concrete, inner core, outer core, and the surface of the steel. So we calibrated this formulation. Of course, we calibrated the heat transfer analysis before. Later, we calibrated the empirical formulation with the finite element simulation. And here you can see that for the inner core, outer core, surface, again for the other section, inner core, outer core, and the embedded steel, we could capture the temperature evolution. Okay, so We're done with the column. Now we go for the beam. The same team, but in the when we were close to design, we had the help from Professor Benjamin Schaefer and Professor Shahab Torabian from Johns Hopkins. So the composite beam we had two sections, back-to-back section, that they were another lip channel attached by self-drill fastener. And then we connected the steel section to the concrete slab using bolts. The reason for that was that we were using thin wall steel section. We cannot weld it because we may burn the steel. So the solution that we had was to use bolts. Here you can see some details. And briefly, the test setup was a 6-point bending test. And here you can see the failure mode and comparison with the finite element analysis. Because I have calibration and then later formulation, so I'm skipping to show all the result of the test. So we perform a 960 simulation of composite column with different lengths, just to give you an idea how long does it take for one model. If you have a model with 3 meters and mesh of 20 millimeter for concrete, the running time until you have the failure mode, it's about 8 hours with the computer if you're using 8 cores of Abacus, okay? So if you have the biggest model that I have was 8 meters, and if you do it with the same computer, probably is more or less 7 days. But I was lucky that I used the HPC and I run the models in a very short time. So we had 5 span, 2 configuration, 2 steel grade, 4 concrete grade. I will explain the concrete modeling later in the next section. And we had 3 height of the section and 3 slab thickness. So we compared the result with Eurocode 4. You can see that the results are falling in the unsafe zone. The reason is that Eurocode 4 doesn't have shear connector that is bolted shear connector. And also Eurocode 4 has a limitation that specifies that the diameter of the thickness of the flange over the diameter of the bolt should be less than 2.5. But here we have something about 6.4 because we are using thin wall section. So we did a push-out test just to measure the shear resistance of the bolt here. And we can see that the result is more close to the parametric study and the finite element. So then we decided to tackle and propose something, formulation for the shear connector, like bolted shear connector within the composite system. So for that, we start in a detailed modeling to have the fracture of bolt, fracture of cold form steel, failure of the concrete. So now I am explaining the bolted section, only bolted material. So this is a coupon that was extracted from a bolt done in TU Delft. We converted the engineering to true stress strain curve using this formulation. And then we calibrated only the coupon test and extracted the information like equivalent plastic strain and triaxiality for this point. And then we draw the triaxiality. But this triaxiality, we only calibrated for the tension region, but for the interaction between tension and pure shear, we have to calibrate it with the shear test of the bolt. Okay, so for the Köppen test, we calibrated the engineering stress strain curve, and for the shear test of the bolt, we also calibrated the failure mode due to the shear and were calibrated by the test. In order to give you a feeling of the modeling, I have two videos here of the shear test and tensile test, including the fracture for the selected bolt. Usually when you have a failure mode due to the shear, you have a cut, is like a smooth surface after the failure. Then we simulated the behavior of concrete, which is so tricky in Abacus. So we had 3 grades, up linear up to 40% of the maximum, and then non-linear. Also, we model the concrete in tension. You see the stress strain behavior and damage variable with the. One thing that need to be taken into account, I propose it in the paper, and almost nowhere I have seen that, is that the compressive behavior of concrete also is mesh dependent. So this is a comparison of compression test of the same material, only I changed the mesh size, and the results are so different. So I propose a modification to model the concrete behavior in compression as a mesh-dependent variable. And here you can see that the compression behavior is well calibrated with the test. And then later, we calibrate the push-out test with about 27 experimental available in the literature. And now we move on to do a parametric study only for push-out tests and the shear connectors. So we had 6 bolts, 5 thickness of cold form steel, 2 grades of steel, and 3 grades for concrete. So we compared the result with the equation according to Eurocode. We expected that the results are not aligned because Eurocode is not for this type of shear connector. So we added a new failure mode because Eurocode for equation for shear connector says that either the failure mode is because of the shear failure of the studs or is because of the crushing of concrete around the studs. But since here we are dealing with the thin wall structure, we have to take into account that the failure mode might be because of the bearing of the hole in the cold form steel, because you're dealing with a very thin wall system. So we consider the resistance of the hole of the cold form according to Eurocode 3, and the result were more or less close. So then we went to modify and propose a new equation for this type of shear connector. So we analyze the different failure mode of the bolted shear connector. So first failure mode, this is a typical failure mode. So first failure mode was because of the crushing of the concrete. And then after that, so this corresponds to point A here. And then after that, we had due to the bearing of the hole. And later at point C, which was the maximum, the failure mode was because of the tearing, okay? Tearing failure mode. So this is our proposal, that we said that we consider a limit for the linear behavior and a certain limit for the maximum non-linear behavior. So if the slippage between steel and concrete was about 0.6 millimeter, we consider it linear. And if the slippage was 6 millimeter, we consider it maximum non-linear, because in the previous slide, you saw that, let's go back. You see that the slippage between steel and concrete is about 25 millimeter. That if we have this slippage in the composite beam, probably due to the deflection, the composite beam already has failed, okay? So we consider 6 millimeter as the maximum. So using this formulation, now we went to propose a design for composite beam. So this design proposal is different than what we have in Eurocode 4. Eurocode 4 says that you have to take 90% of the maximum capacity of one shear connector and do the design according to that. But in our system, we may not reach to the maximum capacity of the shear connector in all shear connectors. So the design that we propose here is based on a slippage between steel and concrete. So, but then another challenge raised, because we need to have the slippage between the steel and concrete in the composite beam. So we propose a new empirical formulation that is based on geometry and material property of this section that can determine the average slippage between the steel and concrete in the location of shear connectors. And then later, we design according to the new design rules and compare the result, which is in a very good agreement with the simulations. Now, composite beam at fire. How much time I have? I have time, right? Okay. We have the same team, but Professor Leroy Gardner also helped us in this section. So we had the very similar composite beam, and we did the fire resistance test. And later, when we opened the furnace the day after, we had the failure due to the fracture of the steel section. So we said, okay, cool, it's a nice image, we can publish the result. But later, when we did the calibration, we realized that, no, we don't have failure mode in the steel section. So then another question raised that, is this really the failure mode or happened during the cooling? So we went for this challenge, to solve this challenge, and then I spent almost 2 years to understand the behavior of cold form steel at elevated temperature in terms of fracture. Later, after understanding that, we did a heat transfer analysis using fluid dynamic simulation to have the temperature in all surface of the steel section. So we extracted adiabatic surface temperature in different locations, and then we export these data to Abacus. Later, we did a heat transfer analysis. We measured the temperature on different location of steel and different thickness of concrete. So here you can see that the heat transfer could capture the temperature evolution in the concrete in a very good manner. And then later, we did the fire resistance test, and we could capture the failure mode in the steel section. And as the final input of this, I can tell you that the failure mode was during the cooling. Again, we did not open the furnace. We went home, we came back in the day after, and we had the failure. Maybe an explosion, who knows, because it was in the afternoon. So the failure mode was during the cooling. So when the steel returned back, we had this crack and this fracture in the steel section. And also we compared the result. This time Eurocode 4 was in a good agreement with the experimental test. So the final section is about joints. The same team. I should say that these two guys are like Superman. I have seen so many laboratory that it's barely you can find so active expert people like these two guys, Miguel and Vidal. So this section is only to see the feasibility of the plug and play joint that we had. So we just wanted to plug it and play, and then we disassemble it to see if this is like this connection works, okay? This is the test setup. This is our laboratory, a corner of our laboratory in University of Coimbra. And then we did 3 repetitions. And you see that the failure mode is because of the deformation of the end plate in all section. Actually, during the first test, before even starting the test, maybe in 1 millimeter of deformation, we just heard that the bolts were just failed. So we did not start even the test and the bolt failed. Apparently the bolts were not really with a good quality. So we went and bought new bolts, and then we assemble it immediately. So we just say well done to each other that our connection can be disassembled and assembled quickly. So later, to do the simulation, because the failure mode was in the end plate, we did not cut the end plate to have Köppen test to have the precise behavior of that steel. But luckily, at that time, I was working with the big boss to propose a formulation that statistically can replicate different grades of steel. So then I said that, why not? Let's do the simulation according to our formulation that we are proposing. So let's see if it works. And then this is the result of the calibration of the finite element with the experimental test. So finally, I explain all this section to come again to the first slide, that this was the system that we proposed and has been accepted as a patent worldwide. The result of this study was published in 22 journal papers and some conferences. So we also have a special issue in Journal of Structures that the bad news is that the deadline is end of the May. If you have works to submit, you have to prepare the work soon. So I'm within the time. It's okay? Yeah. So with this, thank you so much for your attention.
Thank you, Rohola, just on time. We'd like to invite Douglas to give you a gift. Where's Douglas? Ah, I'm sorry. Do you have question? Someone of the audience have question? Professor, the big boss.
No, this is not really a question. The bill for the repair of the furnace is still waiting for your payment.
Is there some other question or commentaries? I don't know.
Hi, congratulations on your presentation, a really interesting topic. My question is more like a curiosity. I wanted to know if the composite columns you tested were also using the lightweight concrete, and if so, the motivation to use this material. Oh, sorry. My question is more like the curiosity. I wanted to know if the composite columns you tested were using the lightweight concrete, and if so, the motivation to use the material, to use this material.
First, let's answer the comments of Professor, and then I will come back to you. Yes, I was promoted after this, and then now I realize that it's like I confess in a police station. Because there is everything recorded that I damaged the electric furnace. So, but come back to your question is that the whole reason of proposing this is to push the lightweight system, okay? And then is not really is like not that we are going to propose something that is lightweight because we have concrete there. But this is, we use concrete to improve the behavior of thin wall. And then the whole idea was to present the system that you saw. So with the concrete, somehow we overcome the challenges that we have in the cold form steel section, which is early buckling failure mode. I don't know if this is your question and this answer is clear. Yeah.
Is there any other question? No.
Just a simple question. I don't know what thickness of material we're talking about.
I'm talking about 1.5 millimeter, 2 millimeter, and maximum 3 millimeter.
Is this galvanized or not?
Yes.
Yes. Okay.
So thank you so much. Now we can invite Douglas. Douglas is here? I don't know, I think. So we will deliver to you a little gift.
It's easy to leave you behind. I don't wanna try.
Pessoal, agora a gente abre espaço para o coffee break. Aí todo mundo pode ir lá para fora, tá bom? Obrigado.